Right, now looking at rates of change in modelled functions. Modelled functions meaning functions that model real life situations. We'll look at a couple of examples in a moment. Just a few things to jot down. I don't know, you might pause the screen here and then come back when things are written down. It's up to you. Make sure you get this stuff. We're looking here at average and instantaneous rates of change. So we're going to look at, we're going to distinguish between the two. We're going to work out how we calculate each. Average rates of change use simple rise-run calculations, so this is not difficult for you. A rate of change, for instance, from on say this model here between these 2 points, the rate of change, the average rate of change, would just be a matter of us working out, joining up the 2 points, and working out what the rise over run is. So we just work out these lengths, do a division. It's gradient, it's rise over run. So that's our average rate of change. Whilst calculus is employed to calculate instantaneous rates of change. So if we want the rate of change on this curve at this point here, as you know, what we need to do is calculate the gradient of the tangent there, and in order to do that, we use calculus. We derive, get the gradient function, it delivers to us the gradient of this curve at that point, blah, blah, blah. Right, that's for instantaneous rates of change. Does that make sense? Instantaneous, at that instant, what's the rate of change? Whereas average rates of change talk about over a distance between 2 points. Okay, let's have a look at an example, and there it is written down here. A diver jumps from a platform at time t equals 0 seconds. The distance of the diver above water level at time t is given by. Right, there's weird numbers here, but that's because the acceleration due to gravity is minus 9.8 meters per second squared, so that's why we've got this minus 4.9. There's a bit of integration involved there. This will become obvious perhaps as we delve deeper into this wonderful world of calculus, where S is in meters. Right, so this is what's going on at t equals 0. We could put in, oh, there we go, put in t equals 0. S is 10. That makes sense. It's a 10-meter platform. Okay, so find the average velocity of the diver over the following time interval. So what we're going to do is develop a little few calculations here and see what's going on. Over the following time interval, so from 1 second to 2 seconds. Okay, the average velocity. So let's go over here and have a look at what average velocity is and how it's calculated. It's the change in distance over the change in time. Makes sense? So let's find out where the diver is at 1 second, where he is after 2 seconds, and then divide by the change in time, which would just be 1 second here. So our calculation is going to be S2. I didn't do a very good job of that. Writing is difficult sometimes. S2 minus S1. So this means where the diver is at 2 seconds, where he is at 1 second, over 2 minus 1. That's the change in time, 2 seconds to 1 second. So let's work this out. S2, I think I've already worked out S1. There's S1 there, that's 10. Alright, so that's minus 10 over 2 minus 1 is 1. I just need to work out S2. So going into the calculator, I'm going to go and select that and hit enter. And then all I've got to do is go back through, because this is minus 4.9. You can see this is minus 4.9 t squared. That's my t squared for when t is 1. Now I want t is 2, so that's times 4. And then I just arrow across here to 4.9 times t, which is now 2, plus 10, I hit enter, that's 0.2. So I go back in here, and I put in 0.2 here. So I've got 0.2 minus 10 over 1, which I believe is minus 9.8. The average velocity is in meters per t is in seconds, meters per second. Right, that is in fact gravity, as an acceleration. Right, so that's the travel between 1 and 2 seconds. The average velocity in that time is minus 9.8 meters per second. Minus because this diver is obviously falling. Now, all right. So let's. Oh, right. What is it between 1 and 1.5? Well, that'll be the diver's height at 1.5 minus the diver's height at 1, all over 1.5 minus 1. Okay, let's work that out. I know what's on the denominator. That's 0.5. I know that it's 10 there for 1. So now I just need to work out at S1.5. So I go back into my calculator and I arrow back up and I select that. I hit enter. Now I go back through here, and in fact now I'm going to put in a little 1.5 squared. Thank you. Minus 4.9 times 1.5 squared plus 4.9 times 1.5, so I'm going to put a 1.5 in there, and then plus 10, and I get 6.325. So I go in here and go 6.325 in minuscule writing. I subtract 10 from that, so I could even go back in here now and say, well, give me that, hit enter. I'm going to subtract 10, hit enter again, divide that by 0.5, and I'm at minus 7.35. Minus 7.35 meters per second. Okay, now we're tightening it up again. We're going between 1 and 1.1. You'll see where this is going in a moment. So we want the read at 1 point. Actually, sorry, I got confused there for a sec. So I want the read at 1.1, the height at 1.1. I want the height at 1. So I'm going to see the change in distance there traveled over 1.1, and this is just 0.1 of a second, isn't it? So I'm dividing by 0.1, and on top here I've got 1.1. So I've got to go back in here and do all this. Don't you just love this stuff? Right, so we go in there and right, let's just get down to 1.5 because that's going to change to 1.1. This is a quick way of doing it. Hopefully you're learning some calculated techniques here, or maybe you knew them already. That's fine. 1.1 goes in there. Enter. 9.461. Remember that. 9.461. I need to subtract 10 from that. So minus 10 equals, divide by, what am I dividing by? 0.1. That's going to be minus 5.39. Minus 5.39 meters per second. So it's still falling, but at a slowing rate. Oh, hang on a sec. Now we're going to look at this tiny little interval here. I want from S 1.01 over 1.01 minus 1. So now I've got 0.01 underneath, and I've got something minus 10, and I need to go in here and find out what it is. And no doubt you're playing this in double speed because it's driving you crazy. So 1.01 goes in there. 4.9, 1.01 goes in there. Hit enter. Now I'm going to take, right, so I'll subtract 10 from that, and I divide by 0.01. Minus 4.949. Minus 4.949 meters per second. Now what's going on here? Look at that. That's in 100th of a second. So are we working towards the instantaneous rate of change, do you think? The instantaneous velocity at t equals 1 second? I think we are. So how do we find that instantaneous velocity? Well, just as we did when we found the gradient of a curve at a point instantaneously, we're going to do the same here. We're going to find s dash t. We're going to find s dash t. So what's that? Let's derive this twice. Minus, that's minus 9.8 t. Minus 9.8 t plus 4.9. Right, now we put t equals 1 in here. So s dash 1, and I'll have the instantaneous rate of change, the instantaneous velocity at 1 second. So in I go with 1 minus 9.8 plus 4.9, and that's equal to minus 4.9 meters per second. Let's see what we got here. We had an average rate of change over a 1 second interval. We narrowed it to a half a second, to a tenth of a second, to a hundredth of a second, and we got closer and closer, didn't we? It's a bit like that process we went through first principles, and we ended up as minus 4.9. That's to 100th or to a tenth of a second, the same as a tenth of a meter per second, the same as the instantaneous velocity. So this was kind of our process that we've been through, and so we get minus 4.9 instantaneous velocity at t equals 1. So there's the process. Average velocity, change in distance over change in time. Instantaneous velocity, use the first derivative, substitute in, and away you go.